Back here again with chapter 18. Now remember we talked about in one of the previous sessions that if you want to do a halogenation on the benzene ring, we use bromine and we also use a catalyst like iron bromide, ferric bromide. Okay. But if you have a strongly activating substituent on the benzene ring, you can do the halogenation without having a catalyst. Okay, halogenation with a strongly activating group present. Halogenation of a ring with a strongly activating substituent like a methoxy group does not require catalyst. You can just add the bromine. So since a strongly activating substituent is an ortho para director, you will see ortho compound and then the para substituents on the benzene ring. Okay, but if you do use a catalyst, you are making the reaction more accelerated, so that will make all the orthopara positions brominated. So methoxybenzene with iron bromide as the catalyst and the bromine, instead of getting either ortho substituent or the para substituent, you get both of the ortho positions will be brominated as well as the para position. Okay. And remember we talk about the Friedel-Crafts acylation and Friedel-Crafts alkylation, meaning addition of alkyl group or acyl group on the benzene ring with Lewis acid catalyst aluminum chloride. But if you do have these compounds to begin with, which is sulfonyl group on the benzene, benzene sulfonic acid and nitrobenzene, what kind of groups are they? Are they activating the benzene ring or deactivating? They are very strong deactivators. Remember, they would withdraw electrons away from the benzene rings. Okay, so as a result, when you have a sulfonyl group or a nitro group, meaning strongly deactivating groups on the benzene ring, they will not undergo Friedel-Crafts alkylation or the Friedel-Crafts acylation. Friedel-Crafts reactions are the slowest of the electrophilic aromatic substitution. Aromatic substitution reactions and do not occur in the ring if it has a meta director, meaning they are deactivators. Okay. Aniline. So this is the molecule aniline. Aniline is benzene with NH2 group. That also does not undergo Friedel-Crafts reactions. Now we know aniline NH2 is a strong activator, meaning through the resonance it can give electrons to the benzene ring and increases the electron density of the benzene ring towards electrophilic aromatic substitution. But here we are saying they do not undergo Friedel-Crafts reaction. Why is that? When we add aluminum chloride to aniline, so this nitrogen lone pair going to act as a base, Lewis base, and give its electron to the aluminum Lewis acid and forms this intermediate, a protonated nitrogen. Remember we talk about now this become a meta director, since this would directly add a positive charge on this carbon that will stabilize the structure. As a result, this is a meta director, meaning it deactivates the benzene ring. So the lone pair on the amine group forms a complex with the catalyst which converts a substituent to a meta director. So meta directors will not undergo Friedel-Crafts reactions because they are deactivating. Aniline must be protected. If you want to do a reaction, we want to make sure that this aniline NH2 group protect before we do a reaction. For example, a nitration. Aniline cannot be nitrated directly because the nitric acid oxidizes NH2 group. This NH2 group, let's say you want to add a nitro group into aniline, but it will oxidize the NH2 and we will not be able to nitrate the ring. So what we're going to do is we're going to react the aniline nitrogen with acyl group, acyl chloride, forming an amide. Now nitric acid and sulfuric acid will not be able to oxidize this group because now it is been protected. Then you can do the nitration, and this is a ortho para director, and ortho position is more hindered, so then the nitro group will go to the para position. After the nitro group is being added, you can add hydrochloric acid. You heat it and then add a base in 2 steps to get rid of the acyl group. It will give you NH2, aniline. Now this process can be used to nitrate aniline by protecting the NH2 group. If the amino group is protected by acetylation, the ring can be nitrated. The acetyl group is removed by acid catalyzed hydrolysis. Now let's see the synthesis of different kinds of aromatic rings, okay, with different substituents. Designing a synthesis. So we want to synthesize this molecule, 2-phenylethanol, and we can achieve this with 2 methods. So this is 2-phenylethanol. So 1, 2, second carbon has a phenyl group. So 2-phenylethanol. First method, you start with a benzene ring. You do bromination in the presence of the catalyst iron bromide. So the bromine will be added. So you use this because we don't have any activating group on the benzene. So the bromine will be added. And then we can make this a cuprate. Remember, we can put a copper between these two and form the cuprate, which we learned how to do in a previous chapter. In the presence of lithium and tetrahydrofuran, and then you add copper iodide, you can create the cuprate with this bromobenzene. That is this one. Now this can act as a nucleophile, and you react this with ethylene oxide, epoxide. So this copper is electropositive, this carbon is electronegative, nucleophile, attack this carbon, open up the carbon-oxygen bond, and then in the second step when you add hydrochloric acid, this oxygen will protonate to give you the 2-phenylethanol. Excuse me, that's one method. Another method would be you react benzene with ethyl bromide and aluminum chloride. So this is the Fiedel-Crafts alkylation. So you add the alkyl group, ethyl group, and then you can brominate this in the presence of the light, bromination, radical bromination. And when you do brominate, remember we talk about only the benzylic carbon, hydrogen on the benzylic carbon will brominate and give this compound. And then you do elimination with a bulky base. So then the hydrogen and bromide will eliminate as HBr and you can form the alkene. Okay, now we want to form an alcohol OH here, which is anti-Markovnikov rule, addition of a water molecule across the double bond using hydroboration. Okay, so BH3THF, and then the second step you add hydrogen peroxide. So then the OH goes to this carbon and hydrogen goes to this. It's an anti-Markovnikov rule, right? And 2-phenylethanol. So there are 2 methods that you can achieve the same product. And when there are 2 routes present, the preferred route depends on the number of steps. So this one has how many steps? 1, 2, 3. And this one has 1, 2, 3, 4. Depending on the number of steps and also the complexity of each reaction and the overall yield. So the first route is preferred because it has less steps in it. Okay. And when you are performing a reaction, the order of the reactions is also important because some of the substituents are orthoparadirectors and some substituents are metadirectors. Let's say you want to form meta-bromo benzene sulfonic acid from benzene. Okay, in order to do that, we have to put a bromine group on the meta to the sulfonyl group. And this sulfonyl group is meta to the bromine. Now, if you look at the 2 substituents, this is a sulfonyl group, this is a bromine. So, bromine halogens, are they orthoparadirectors or metadirectors? Halogens are orthoparadirectors and the sulfonyl groups are metadirectors. So if you first put the bromine, we will not be able to put the sulfonyl group on the meta position. But if you do the sulfonation first, since it's a metadirector, then you can add the bromine to the meta. Okay, So because of that, we first do the sulfonation, adding sulfuric acid and heat, make benzene sulfonic acid, and then when you do the bromination, bromine with iron bromide, so this can go to the meta position, meta-bromobenzene sulfonic acid. Okay, and then if you do want to make a para-bromobenzene sulfonic acid, then you have to reverse the order. You first do the bromination. Bromine is orthopara. So then you do the sulfonation. You can have the mixture of products, meta product as well as ortho product. Okay. The role of the reaction is important. Another example, you want to make a meta-nitroacetophenone. Okay, so this group over here, a nitro group, it's a meta director. Okay, a carbonyl group. Okay, so what we're going to do is, if we add the nitro group first, then it would not undergo Friedel-Crafts acylation. So we're going to put acyl group first, the Friedel-Crafts acylation. So benzene ring with acetyl chloride. In the presence of aluminum chloride catalyst and water, we can add the acyl group. And then when you add the nitric acid and sulfuric acid to generate the nitronium ion, it will add on to the meta position, meta-nitroacetophenone. The acetyl group must be added first because Friedel-Crafts acylation will not occur if there is a meta director on the ring. Okay, so that's why we first put the acetyl group and then the nitration. Now there are two cases. So one here, para-chlorobenzoic acid. This is meta-chlorobenzoic acid. How are we going to make them? To make the para-chlorobenzoic acid, what we're going to do is, first you can start with toluene. It's commercially available. Toluene, you add chlorine with iron chloride. So then this would add on to the para position. We will also get some ortho product also, but since this is the final product we want, let's assume it goes to this position. And then you do oxidation. What happened to the alkyl group when you oxidize? It becomes a carboxylic acid. We learned about this earlier. So that's how you make para-chlorobenzoic acid. But how do you make meta-chlorobenzoic acid? You still start with the toluene. Now you do the oxidation first. Okay, when you oxidize alkyl group, it will become carboxylic acid. Now the carboxylic acids are meta directors. Then you add chlorine with iron chloride, it will go to the meta position. That is the meta-chlorobenzoic acid. Okay. Let's say you want to synthesize this molecule, meta-dipropylbenzene. So we need to add two propyl groups on meta to each other starting from benzene. But these alkyl groups, are they meta directors? No, they are orthopara directors. So let's see how we can put them on meta position. Okay. First thing, you use the Friedel-Crafts acylation on benzene ring. Excuse me. Starting with propanoyl chloride, because we need 3 carbons, 1, 2, 3. So you use acetyl chloride, not acetyl chloride, propanyl chloride, acyl chloride with 3 carbons, 1, 2, 3. So then you have this compound. So this molecule. And then when you add bromine with alkyl iron bromide, now this is a meta director with the carbonyl group. Okay, meta director, remember you can refer to the chart in an earlier slide if you have forgotten. So this is a meta director, so the bromine will add on to the meta position. Okay, And then when you add hydrogen palladium carbon, which is reductive hydrogen reducing agent for the hydrogenation, you're going to reduce the carbonyl group to CH2. Now still we have a bromine there. So how do we make another propyl group? We can do the Suzuki coupling. We talked about Suzuki coupling earlier, the bromobenzene with boron complex, two alkoxy groups, and then the corresponding alkyl group. When you couple these two together in the presence of palladium ligand and sodium hydroxide, the bromide will be replaced with the propyl group. That's how you can make meta-dipropyl benzene. First alkyl group is added by Friedel-Crafts reaction. Friedel-Crafts reactions will not work with a meta director on the ring. Okay, so the second alkyl group must be added by a coupling reaction. That's what we did. Another one. So let's say you want to synthesize a para-propyl benzene sulfonic acid. Sulfonic acid, para to the sulfonic acid, you have a propyl group. Now, if you add the sulfonyl group first, so this is a meta director, we will not be able to add into the para position. So we have to first add the alkyl group. We can do the Friedel-Crafts acylation with propanoyl chloride, adds the propanoyl group onto the benzene ring, do the reduction, carbonyl group to CH2 using hydrogen palladium carbon. Now the alkyl group, you can do sulfonation with sulfuric acid, and this is a orthopara director, so we can add it into the para position. You will also get some ortho product, but mostly would be majority of product would be para position sulfonation because of the steric hindrance at the ortho position. Okay. So another method to achieve the same product, starting with benzene, you brominate it with bromine and iron bromide, and then you do the Suzuki coupling. Okay, to achieve this same product, you use this compound, boron compound with the propyl group and alkoxy group, palladium catalyst and sodium hydroxide. So this will replace by the propyl group, and then you do the same thing with sulfonation. We can get it the para-propyl benzene sulfonic acid. To synthesize one compound, you might come up with different routes. The synthesis of tri-substituted benzene, meaning we need to have 3 substituents. Now, when you try to do that, we need to be careful and find out whether the existing substituents are orthopara directors or meta directors, and which one is going to be the one that determine where the incoming substituent gonna go. Okay. The directing effects of both substituents must be considered in deciding where the third group will add. Now here you have a methyl group and a nitro group. So methyl is an activating group. So it normally adds to the ortho and the para position. But the para position already has a nitro group. So methyl group normally adds to ortho position. And with regard to nitro is a deactivating group. So it adds substituents to the meta position, not here. So then for the nitro also it prefers meta. So in this case it doesn't matter, the product is going to be either here or here, because both of these, if you look at individually, they would prefer this position. So the nitration will give us the product nitration either this position or here. Both substituents direct to the same position. Now in this one, a methyl group is an orthopara director. So according to the methyl, the incoming group can go to here, here or here, orthopara. Now with regard to chlorine, chlorine also an orthopara director. So these two positions are ortho to chlorine and this is para to chlorine. So when you do a nitration, it would go to the place where it least sterically hindered. So it can either go to here, here, or here. Okay, so then we will see these two as the major products, not many over here, since it's between the two groups, and the steric hindrance will inhibit coming the nitration over here. Both substituents react to the same position. Addition between the two substituents is a minor product because of the steric hindrance. Another one. So you have two substituents. Alcohol OH group is orthopara. It can go either here or here. And then the methyl also orthopara. Now, if OH group predominates, then the the bromination should happen over here. If it is methyl, then it should happen the bromination at this position. Okay. Both substituents direct to different positions. So then the strong activator wins. So between OH and methyl, methyl is activated through the induction, OH is activation through the resonance. So the OH is a more stronger activator. So then the incoming electrophile goes to the ortho to the alcohol group, OH group, which is the major product. And now here you have a methyl and an ethyl. So these two, so methyl, ethyl, they are orthopara directors. These two are ortho to this one, and these two are ortho to this guy. Okay, so both substituents direct to different positions. The similar directing ability of the group leads to addition at both positions. So there is not much of a difference between the methyl and the ethyl. Similar activation through induction. So we will get a mixture of both positions. Okay, nitration at both positions. This is ortho to this group. This one ortho to this. Okay. This is another interesting section. We'll start this session in a new lesson.